Hello, everyone. Today we're going to begin Unit 10 on thermochemistry. We're going to start by talking about molar heat capacity and specific heat. For those of you who are paying close attention, you'll notice that we skipped over Unit 9. Unit 9 is traditionally on solutions. We talked briefly about molarity, and that's the most important part that I wanted you to get out of the solutions unit. We combined that back in stoichiometry. I wanted to make sure that we got to talk about the heat energy that's involved in chemical reactions. So that's why we're skipping ahead to Unit 10. In this unit, we're going to focus on the heat evolved or required for a chemical reaction to occur. We're going to take a look at phase change diagrams, heating curves, and start to relate chemical reactions and stoichiometry to the amount of heat energy either given off or required for a chemical reaction to occur. Now, let's begin by taking a look at today's lesson on molar heat capacity and specific heat. We're going to start by looking at two different directions that heat can go in a chemical reaction, either into the reaction, allowing it to occur, or heat could be given off as a result of a chemical reaction occurring. Think about a combustion reaction and the burning of gasoline. That releases a tremendous amount of heat. That's an example of an exothermic, because heat is leaving the system, an exothermic chemical reaction. There are other reactions that take place only when heat is added. So if you think about that, that's an endothermic, meaning heat is coming into the system in order for that chemical reaction to occur. Now, if we're looking at this in terms of an equation, this is how it would be written. In an exothermic reaction where heat is given off, heat would be included on the product side. In an endothermic reaction where heat is needed in order for a reaction to occur, we would treat heat as another reactant, and it would be written on the left side. The easiest way to remember this is by looking at the prefixes. So En, that sounds like the word that we use for entering. So if we use that same analogy for heat that is leaving, we use the prefix EX, like heat is leaving the chemical reaction, or heat is being given off as a result of this chemical reaction. Okay, let's take a closer look at each of these graphs. If we look at the graph on the left side, the endothermic reaction graph, I want to start by labeling the different plateaus on the graph. So the amount of energy that we start with all the way on the left side here is known as the energy of the reactants. The energy that we finish with, where this letter C is representing our products, that's known as the energy of the products. The difference between those two energies, which is being represented by this arrow here, is known as the energy of the reaction. So I'm just going to jot down those terms. Once again, all the way on the left side, just like the left side of the equation, we have the energy of reactants. On the right side of the graph, just like we have on the right side of the equation, we have our energy of products. And finally, the difference between the amount of energy at the beginning and the amount of energy at the end is known as the energy of the reaction. We can label the same points on our second graph. So once again, we'll have energy of the reactants. We'll have energy of the products. finally, energy of the reaction. Now, some of you may be wondering what that little hill is in the beginning of the chemical reaction. So if you think about something, think about lighting a can of gasoline on fire. You have to provide that source of ignition. So if you're striking a match and then lighting a vat of gasoline on fire, you're providing the activation energy for that reaction to occur. Even though the reaction itself produces a tremendous amount of energy, you need to put in just a little bit in order to get it started. That is called the activation energy, and that is what is being represented by this difference in energy here. So this is our activation energy. For an endothermic reaction, that activation energy is much greater. Okay, let's take a look at how we're going to use some of this information in some equations. So, as you know from the title of this lesson, today we're going to focus on molar heat capacity and specific heat. And we're going to be looking at these two equations in particular. Now, both of them are ways to calculate the amount of heat energy associated with a particular substance. So before we start talking about reactions, we're going to identify the heat energy of a single substance changing temperature. So if we do that, we're going to first identify all of our different variables. So in each of these cases, all the way on the left side, we have our energy. And energy, some of you may know, is measured in joules. So we have our energy in joules. Now, in the case of the molar heat capacity equation, molar heat capacity sounds like what other word that we've learned? Moles, hopefully. So in this equation, just like we saw in PV equals nRT, N is going to represent the number of moles. In our specific heat capacity equation, instead of having moles, we have an M. And an M is going to represent mass. And instead of it being in units of moles, like we would see up here, we're going to have mass in units of grams. The next part, the C in both of these equations, stands for a constant. So the constant in terms of the top one is called the molar heat capacity constant. And in the case of the bottom one, it is called the specific heat capacity constant. These constants are a measure of how easily a substance will absorb or release heat. It turns out that the substances that absorb heat very readily also release that heat very readily. Here's an example. If you imagine sitting down on an iron park bench in the middle of summer. The park bench has been in sunlight all day and is extremely hot. As soon as the sun goes down, that park bench will cool off very quickly. Now, compare that with something like a swimming pool. So in a hot June day, after the sun has been shining on a swimming pool, you might jump in and find that the water is still really cold. That's because that one day of sunlight isn't really enough to warm up the temperature of water. Instead, you might notice that in late August, early September, even late September, the temperature of water in that pool is still very warm because it's been heating up all summer. So water takes much more energy to heat up, but also cools down a lot slower than something like a piece of iron. So we would say that the specific heat capacity of water is much greater than the specific heat capacity of iron. Iron heats up very quickly, cools off very quickly. This is also why we use things like iron and copper and other metals to make pots and pans. A pot or pan wouldn't be very useful to us if it took a half an hour just for the pan to heat up. So keep in mind that the higher the specific heat constant or the molar heat capacity constant is, the longer it takes for that substance to heat up, the longer it takes for that substance to cool down. In addition, the molar heat capacity constant shows you how much energy is absorbed and how much energy is released. So water is going to absorb a tremendous amount of energy, and it's going to hold on to that energy for a longer period of time and then release that energy very slowly. Let's take a look at our thermometers on the side. If you notice, we have three different scales here: Fahrenheit, Celsius, and Kelvin. I'm going to ignore the Fahrenheit thermometer for today. Instead, what I want to focus on is the Celsius and Kelvin temperatures. Now, if you look back at our equation, we didn't talk about our last term, but our last term is delta T. Now, in math and science, delta means change in. So delta T is going to mean change in temperature. So for the first equation, we're going to measure change in temperature in units of Kelvin. For the second equation, we're going to measure change in temperature in units of Celsius. The nice part is, unlike when we were learning gas laws, it really doesn't matter what unit we use for change in temperature. And here's why. If you think about the freezing point and the boiling point of water, 0 degrees Celsius and 100 degrees Celsius, there is 100 degrees between those 2 points. So here is our freezing point of water, here's our boiling point of water, and the difference between these two is 100 degrees Celsius. Now, if we were to think about those two temperatures in Kelvin by adding 273, we would get 273 Kelvin and 373 Kelvin, or a difference of 100 Kelvin. That's because the unit size in degrees Celsius is equal to the unit size in Kelvin. Therefore, when we're talking about changes in temperature, not temperatures themselves, but the difference between two temperatures, those differences are going to be the same regardless of whether you're using the Celsius scale or the Kelvin scale. Okay, let's take a look now at our first three problems. Now, I'm going to do something similar to what I did in our last homework assignment. I'd like you to open up the homework assignment right now, pause the video. We're going to go through the answers to the first three problems on the homework assignment together, and then I'm going to ask you to finish the remaining four problems later on your own time. Let's take a look at our first example. It says, calculate the energy needed to raise the temperature of 180 grams of water from 10 degrees Celsius to 40 degrees Celsius. And it gives you the molar heat capacity for water. Now, this is a bit of a trick question because you're given 180 grams of water, yet you're given a molar heat capacity constant. So what we need to do in order to use that molar heat capacity constant is to take our grams of water and convert it into moles of water. Luckily, we've been doing this for several weeks now, so we know how to do that very easily. So I'm going to begin by listing my givens on the side: Q, N, C, and delta T. Again, we're using moles and not grams because the constant that is given to us, 75.3 joules per Kelvin mole, uses moles. Let's take a look at our difference in temperature. We go from 10 degrees up to 40 degrees. That's a difference of 30 degrees Celsius. So remember, if we're talking about a change in temperature, that's different than a temperature by itself. If we're talking about a change in temperature, so going from 10 up to 40, that's a difference of 30 degrees Celsius, which is equal to 30 Kelvin. Finally, in order for us to use this equation, we're going to have to convert our 180.0 grams of water into moles of water. So we have 1 mole of water, 18.02 grams of water. We wind up with the number of moles of water equal to 9.989 moles of water. So we can put that right here. So in this problem, we're looking to solve for Q, our heat energy for this problem. To do this, we're simply going to multiply all of these together according to our equation, N, C, and delta T. So we're going to have 9.989 moles times our molar heat capacity constant, 75.3 joules per Kelvin mole, times our delta T, which is going to be 30.0 Kelvin. Lost a significant figure here. I'm just going to put that back. Okay, typing this into our calculator, we have 9.989 times 75.3 times our 30 Kelvin temperature difference. We get an answer of 22,000, and it is very common for Q values that are measured in joules to be really large, so don't be thrown off. 22,000, and we're limited to 3 significant figures. So we're going to go with 22,600 joules. In this case, because energy is being absorbed, we're using energy to raise the temperature of something, the value for Q is going to be positive. Now, you don't have to write the positive sign there, but in an example where heat is being released and we have to indicate that with a negative sign, you would be required to write the negative sign in those cases. Let's take a look at a second problem. In our second problem, it says how much energy is released when 147 grams of water cools. So now our Q value is going to be negative, cools from 90 degrees Celsius to 17 degrees Celsius. And this time they give us a specific heat capacity in joules per gram. So we're going to use mass when we look at our formula. Q M C delta T. We're once again solving for heat energy. We have a mass of 147 grams. We cooled from 90 degrees Celsius down to 17 degrees Celsius, or a difference of 73.0 Celsius degrees. And we're given our specific heat of water as 4.184 joules over gram degrees Celsius. Once again, we can plug into our equation, Q equals MC delta T. We don't need to rearrange it since we're solving for Q. We have our mass, 147 grams, times our specific heat capacity constant for water, which is joules, 4.184 joules per gram degrees Celsius, times our change in temperature, which in this problem is 73.0 degrees Celsius. Typing all of this into our calculator, we have 147 times 4.184 times 73. We get this answer. Now, again, a very large answer for Q. So 44,000 We're going to keep just 3 significant figures. So I'm going to round that to 44,900 joules. However, because the temperature is going down, because energy is being released as a result of this change, we have to include a negative sign here. So our final answer is negative 44,900 joules. Negative again, because energy is being released. We know energy is being released because our temperature is coming down. Let's take a look at our third and final example problem. In this example, we once again are using Q, M, C, and delta T. We know that because it mentions the words specific heat constant as opposed to molar heat constant. Now, it says a substance with a mass of 35.5 grams, so we're given the mass right in the beginning of the problem, absorbs, so we know that Q is going to be a positive number, 48.6 joules of energy as the temperature goes from 293.2 Kelvin up to 316.1 Kelvin. So our change in temperature is going to be 316.1 minus 293.2, or a difference of 22.9 Kelvin. Now, keep in mind, usually when we talk about specific heat constants, it's joules per gram degrees Celsius. So really, this temperature change needs to be in degrees Celsius. Luckily, as we talked about before, because we're talking about a change in energy and a change in temperature, this is going to be equal to 22.9 degrees Celsius. So if we were looking for a temperature, we would have to worry about converting between Celsius and Kelvin. Because we're talking about a change in temperature and the unit sizes are the same, it is equal to the change in Kelvin. So we're going to begin with our traditional equation, Q equals mc delta T. This time we're solving for C. So C is going to equal Q divided by M times delta T. Keep in mind, because we have these two numbers being multiplied in the denominator, you have to include them in parentheses when you're typing them into your calculator, or remember to hit divided by before you enter in each term. So in this case, we have 48.6 divided by our mass, 35.5, also divided by our temperature change, 22.9. We wind up with a really small answer for C. C is equal to 0.0598 joules over gram degrees Celsius. It is quite common for the value for specific heat constant to be really small, just like it's quite common for the value for Q, heat energy that we're measuring in joules, to be really large. Okay, please try the 4 remaining problems on this assignment for homework. Please let me know if you have any questions, either through a message on Schoology or by stopping by during office hours. Have a great week, everyone.